All right, but today's topic is actually about the systems, and what I'm trying to do is cover both the system fundamentals and also system responses on the same day. So you need to leave at 3:15 or something like that for a class. Okay, that shouldn't be a problem. But I really hate to rush through these things since this is quite, say, quite important matter here. Okay, so about the digital system fundamentals, the basic operations on digital signal processing, there are only four. Add, scale, meaning multiplying with the scalar, a number, a constant number, and then delay, and then mix, meaning the multiplying signals. Okay, that's it. That's all what are needed. Here I have the mathematical symbols and then also the block diagram symbols that I use. There are some variations on, especially on the block diagrams, how they are used. Well, the mathematics is a international language. I think it's the only really international language. But on the block diagrams, there are local variations. And also, well, when you go into this software engineering, then you have all sorts of different ways of describing a program using some sort of blocks. Okay, but anyways, I'm using those. And let's go a little bit forward. First of all, the fundamental properties of systems. So these are basically, four different properties that the systems share no matter what. And this actually is a list of just, say, neutral properties. For example, a system can be nonlinear and still good system. Same goes with the causality, stability, and time shift invariance. So this is not about list of good and bad. This is just a list of, say, properties without any further, say, emotional feeling. So first of all, let's see, do I have that? Okay, yeah. Linearity. Linearity, basically what it means that if you have a linear system, then it's also you can apply the superposition principle, meaning basically if you go into the block diagrams, on the block diagram level, let me see if I can actually put this one on 4 parts. So linear systems, we have, let's see, what does it say? A system. This is our system, which has some function, okay, function f, does something for the input signal. So what that superposition principle actually means, that if you have a signal going in which is combined by 2 weighted signals, any arbitrary 2 weighted signals, x1 and x2, and weighted with different scaling parameters, then what comes out should be actually A times the signal 1 output plus B times the signal 2 output. Okay. So you can actually separate these different signals and feed through the system and sum the output. It's exactly the same. Okay. So that actually means that the system would be same as having the x1 in one of the systems, another one here. So we have exactly the same system here. And then a gain by A and B. And that should be actually exactly the same. So if a system is linear, that's fine. That's something that we can actually test quite easily. Engineering style, meaning empirical, based on brute force and no math. Well, this is math enough. So what we can do, we can actually take two arbitrary signals, meaning random sequences, and two random multipliers, and try this one if the system output for that one is the same as system output of that. Okay, that should be the same. And question mark. So brute force test actually works pretty well on this linearity test. Next one is causality. System is causal if there is a good reason for the output, meaning no effect before action, no reaction before action. Fundamentally means that if we have a signal which starts at point 0, any signal can be random, okay, all zeros that way. This is our input for the system. Okay, and what comes out is also a system which has all zeros before the time point 0. Basically, this one does not matter. So we need to just check if there is any signals before the input starts. Again, we can do a brute force test. By the way, these brute force tests are not perfect tests, meaning that if you show these to mathematician, he says, ha ha ha, that doesn't prove anything. Well, the same way you know the climate change, ha ha ha. There's no climate change, it's fake news. Yeah, I'm not getting started on that one. But anyway, so causal means that no reaction before the action. Okay. Linear, causal, then stable. Stability. Meaning that if we have a bounded input, meaning for x of n, we have some upper bound, lower bound, bx minus bx, and the signal is somewhere here. We put this signal through the system. What comes out is a signal which has also bounds. Some other bounds, but still by minus by. The signal is still within these bounds, which is really, actually this is a nice property. Again, you know, if we're looking at this, say, good or bad things, maybe the stability thing is something that can be said, okay, it's a good property to have a stable system. This testing of this one is easiest to for our systems, which are almost always linear. time shift invariant systems, basically the testing is done on a zero pole plot. That's the easiest one. Then the third one is time shift invariance. Oops. What does that one actually mean? If we have a signal and we apply a time shift delay in, well, say k times some delay, and we feed through the system, what comes out, and then we basically do first feed the input to the system, then do the delay. They should be actually exactly the same. So you can actually, on the time shift invariant system, you can move the delay on either side of the system. It works the same. Also, this is the same as the system does not use time. So it doesn't have the internal clock. This is not a parking meter. Parking meters are not time shift invariant, since, you know, on nighttime usually you don't have to pay at all. On the beginning of morning starts, then you need to put some coins or drive your car somewhere else. Okay, so again, a property, but on, say, this time shift invariant system they don't change by time, kind of static systems. And again, brute force. We can try arbitrary signal, put a arbitrary delay to it, feed through the system, okay, then do the same thing, put signal into the system, and then do the arbitrary, the same delay, and check the outputs. Are they the same? Okay. Actually, what I could do is to take a photograph of that one. That basically came out pretty well. All right. So, yeah, linearity, causality, stability, time shift invariance. Take a look at this spelling. It's not casual, it's causal. Casual means, well, this is casual. Well, t-shirt, with a t-shirt, even more casual. Causal, okay, reaction happens only after the action. Good. Then about the describing this system. If a system is linear and time shift invariant, then we basically can show the system as a simple difference equation. All of these linear time shift invariant systems can be shown as difference equation. And most of the systems actually are linear and time shift invariant, especially the linear digital filters. There also are non-linear filters which are pretty good on some cases, like the median filter. Median filters are used especially on the image processing, and yeah, they are good filters. But if a system is LTI, linear and time shift invariant, Then we can actually describe the system in the difference equation. Where a sum goes from 0 to capital N, a k, so these are basically the multiplying factors for the output and the delayed parts of it. And the other side is k from 0 to some other number m. Usually those are actually the same numbers, but anyways, b k times x n minus k. So okay, let's take a closer look what we have here. So those are a and b. These are called system coefficients or filter parameters. Or if it's a filter, then those are the filter parameters. And these are actually constant numbers, weighting parameters, constants. Okay, then we have the actually that's the output and delay. This here is the input and delay, meaning that basically, okay, okay, let's not go there yet. This actually is usually the difference equation is marked as the how to calculate the current value, y of n. Y of n is the current value. As a weighted sum of input minus weighted sum of k from 1 to, okay, that's m, n, a, k, delayed output, previous values. So that's a current value. This is the current input value plus the history, the previous values, and this is the history of output, meaning feedback. Okay, so this is the feedback. And that's feed forward part. If we do the, let's see, is it the same one? Difference equation, no, that's an example. Okay, well, maybe we will do the example now. So on the example, I have the 4-point running average filter, which is really rude filtering, but it works. We can actually make this one either so that we don't have anything in here. So all the AKs are 0, meaning this is the forward way of doing it. Straightforward way, we take 4 subsequent samples of input and then basically just calculate the average of those and then move to next value. Get one value in and calculate it again. Okay. So that example actually here means if you have an x and, for example, something like this, we take these 4 values and calculate the average of those to get y of 0. Next one would be calculate y of 1 here. Next one actually goes from here to there, y of 1, 2. Okay. So basically taking those values and then just brute force calculations and moving on. While using feedback, we're actually doing like, think of a table where we have the x0, x1, x2, x3, x4, x5. I think that's enough. First, when we have first calculate the average using this one, we know y of 0 by calculating from there. What we can then do is subtract 1/4 of that one. So for y0 or y1, we actually use the previous value y0, take off that value 1/4 of x of 0, and then add that value 1/4 of x of 4. Okay. Using feedback, the previous calculated output value makes a big difference when you have, say, 100 points. Instead of calculating 100 points average, you just calculate, 3 different calculations. Okay, yeah. A block diagram. Block diagram of that one. Very simple. This is a good place to start drawing the block diagram. So we have output y of n. Then we have one single input, x of n. And everything has to be happening here. This is our system. The system have the system coefficients, b's and a's. Yeah. And then it also have the time shift. All of those are inside. So basically, I can arrange this one in the way that first, let's see, I'll take, since here we have x of n already, we can make a delay chain here, 1 time step delays, as many as needed here. So in this step we have, so this is x of n, this is x of n minus 1, and so on. And then I can put these weights. Here we have B0, B1, scaling factors B2, and so on in here. Then we calculate the sum. For example, this way. So whatever we have here, it's counted as a sum up to this point. So after this point, we have the forward terms. Okay, from 0 to n, m, p, k, x, n minus k is right here. We can do the same thing also for these feedback terms, since we know that at this point we have the current output, which means that if we take the current output, we can always save it to the next round on a delay chain. So here we have yn minus 1, yn minus 2, and so on. And all of these values actually have their own multiplying factors, a1, a2, and so on. And this is a sum again, same way as this feed-forward system. We can actually put these similar summing junction chain. And here, just make sure that you have plus input and minus input. Whoops. So we are subtracting this part from the feed-forward term. So that's how it looks like a system which is direct form 1. Direct form 1 system. Good. And yeah, for this 4-point running average filter implementation, we had only the forward term, or then we also have the feedback term, the one which is oh, wait a minute. Okay. Since we have these multiplications here, okay, we have the common multiplier. It makes a lot of sense to take the common multiplier on the other side of this delay. Then you have to multiply it only once, and then you get the output. Or it's also a third way. Okay, haha. How did that one happen? There's only 2 sums. Okay, yeah, actually that makes sense. That makes a lot of sense. So there's the previous term, and then there's the 1 quarter of the current term is added here. Then this is the delay of 4, so this is the xn minus 4, which is subtracted. So yeah, that's how you do it. Basically, okay, we have this difference equation. Difference equation is nothing more than a mathematical formula that can be used to calculate the current value, but most often it's not the way you would like to calculate the current output. The block diagram is actually the what you should do. This should be the starting point for your program. Not this, not the difference equation. Since sometimes you are missing something on the this difference equation. That's the correct place to start. I will give you an example why it's so different. Okay. I should have another whiteboard now. Oh, I do have. Just use the paper. I already know that this system is linear, which means that actually linear is a kind of nice system, since then you can basically take this part and move it here and this part and move it there. So we transpose the system. x of n, still y of n, but k. Then we actually have this part here, meaning that we have the delay chain at the middle, and these sums, okay, summing junctions in here. And then we have the other delay, or do we? Haha. A trick happens. Okay, B0, B1, B2. Okay. See, we have the same signal here. So we do not need another the delay chain. We just need to take these, move these tabs to the same delay chain. What is the difference? This is actually requiring half. Okay. So don't take that this difference equation as the primary source for your implementation, but think of a different ways to make the system, say, more efficient. Very important thing when you are actually designing these embedded systems filters. In small processors, you never have enough of memory. Never. Right. Transfer function. On mathematics class, have you already covered the Z transform? Z transform, is it familiar? Laplace transform? Laplace transform. Yes, you have covered the Laplace transform. Okay, haha. Z transform actually is a generic or general form to describe a system on frequency space. And I start with the difference equation, that form. So remember the on analog electronics, when you have the system transfer function, or a, well, that's the general form of frequency response. How to calculate these things on analog systems? You have H of S or G of S. Actually, so that you have the Laplace transform of the output is same as the system response, or the transfer functions type times the Laplace transform of the input. Right. You hated that one. I did that. At least I did when I was a student. So awkward way of calculating simple things. Okay. Or basically going to the frequency space, it means that if you want to know the spectrum of your output, it's basically the same as the frequency response of the systems times the times the spectrum of the input. So filtering is fundamentally only a matter of how to do this multiplication. You have the frequency response, for example, like this for low pass filter, h of omega. So whatever your system frequency response, not system, but the signal spectrum is, you basically on output you have only the low frequency terms. Okay, for on if you have a low pass filter. Okay. Does it remind you of something? Maybe. Okay, for discrete time systems, instead of this Laplace transform, so here the for example, x of s is the Laplace transform of x of t. And that's basically the only way you can analyze a system, how it actually is functioning for your test signal. For example, square square wave. Does it remind you something? You have compared the system response using square wave generator and the edge, how it fits with the theoretical calculations, and there you have used the Laplace transform. Right? Maybe. So how many years you have been studying? This is your third year. Okay. Yeah, you have been studying that. That's usually on first year on the laboratories. Maybe not. But anyways, nothing to worry. On analog systems, the transfer function is quite hard to handle, especially without tools. But in the digital systems or discrete time systems, we basically take the Laplace transform, and that actually goes to the Z transform. There's some theory how to do it. It's basically the same thing. It's just sampled Laplace transform, basically. And the system transfer function has exactly the same thing. If you want to know the output, so think of a output which has, system x of n going in. You have a linear time invariant system with a function of something. You have y of n going out. It works exactly the same for Z transform signals. Z transform of x of n comes in, and Z transform of y of n goes out. And for the systems which are linear and time invariant, it just appears that we have the, all right, how to mark this one? Okay, h of z, which is the system transfer function. Times x of n, Z transform. Okay. So this function here is actually, the system is described by the h of z. And with some mathematics, it comes out that for the linear time invariant system with that sort of the difference equation, you have this system transfer function is simply sum of bk times z to minus k divided by k from 0 to n ak times z to minus k. Okay, meaning system coefficients or filter parameters are also describing the system in spectrum space. Not only in the time space, but also the same parameters actually are on the discrete time system on the frequency space. That's really handy. You don't need to actually do the calculations in between. You just need to know the system coefficients and you immediately know how the system behaves on frequency space. Okay, same thing as for analog systems when you have basically the S, the Laplace transformed, you have the system, the frequency response. You get the frequency response by simply, I think it's j omega here. Okay, you just replace that S with the e to minus j omega. No, S equals to j omega. Okay. Same thing here. If you want to have the frequency response, you just replace z with the e to j omega. Okay, let's see how far it is. All right, so Z transform. Convolution. Okay, convolution actually tells you this one. This is how you calculate convolution in frequency space. It's a multiplication of the transfer function times Z transform of x of n. But we do not need to do that in frequency space, since we also have the same thing for time space. This multiplication in frequency space comes as the convolution in the time space. So that's the linear convolution. Yesterday I mentioned about the convolution and also what is a correlation. So correlation is find the match. Convolution is simply calculating these weighted values. This one actually calculates what comes out when you have the impulse response of the system, what comes out for that particular input, meaning the convolution equals filtering. So that's actually here filtering, as we can see here. This is filtering. Right, and there's the summing form of that one. But okay, in frequency space, it means multiplication. Multiplication of the system frequency response with the spectrum of the data. Okay, What next? Transfer function properties, linear time shift invariant. No, not time shift. Actually, time shift comes after z minus k, and then those are the those are for the mathematicians or for the advanced course, and that's basically just proving that when we start from difference equation, we end up having this kind of a transfer function. So h of z equals k from 0 to n, bk, z2 minus k divided by that one. Okay, if you take a closer look at that one, it actually is a rational polynomial of z, although this is a negative polynomial coefficients, but that's not a big deal. It's still a rational polynomial of z. This is the numerator polynomial for describing the feed-forward terms, and then we have the denominator polynomial describing the feedback terms. Okay, good. 4-point running average filter. Again, we had the same coefficients for the difference equation and the transfer function, meaning that okay, so we trend that's one way of doing it. What comes out is we just take a look at the difference equation of the this 4-point running average filter. We had, see example, difference equation y of n equals 1/4 of x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3. It seems that we have if you would just do simple comparison, A0 is the term which multiplies the no delay term of output, which is 1 in most cases. Okay, down here we have 1. And on upstairs we have B0 is 1/4. B1 is multiplying this term. That's also 1/4. Same here. So we have 1/4. And then we have z to power of 0 plus z to power of -1 plus z to -2 plus z to -3. Okay, so the transfer function is exactly that one. Yes, it is. Okay. Or, okay, that's the transfer function for the this system which is based on the feedback. Then we had the difference equation was a little bit different. And actually there we had the difference equation y of n equals the previous value plus 1/4 of the current that value plus 1/4 of xn minus, no, not xn more. There, the feed so this is the feedback of the form of running average filter. Okay, we have now term, not just term, the A0, but we also have A1, which is -1. Why minus? Well, think of the difference equation on that way. So when you move that one on the other side of the equation, then it comes minus. So basically, you have on denominator you have 1 minus z2 minus 1. Yes, which means that you also have to multiply the well, you don't have to, but that's one way of doing it. What we have, I think I have a mistake in here. Yeah. That should be minus x minus 4. Yeah, that has a mistake on it. But anyways, they still match the idea. Transfer function actually can also be arranged as long as you don't change it. Here I have just multiplied it with the same numerator and actually multiplied by 1, which actually is formed by this nice 1 minus z minus 1 polynomial. And upstairs I would have the 1 minus z2 minus 4. Okay, that's the sign error. And downstairs I have this one. And it still shows the same system, but it now matches with the feedback version of the running average filter. Good. Zeros and poles. Transfer function of LTI system is a rational polynomial z. Yes, it is. Let me clean the table. I start from here. This is also the same as if you multiply both upstairs and downstairs, and I will make it a little bit easier for myself. I can make these the same polynomial number because I can actually fix some of these terms as 0. Just this is kind of marking kind of thing. So what I can do, I can actually multiply both upstairs and downstairs by z to power of n. So now I have positive polynomial coefficients. So I have the k from 0 to n, bk, z to n minus k, and k from 0 to n, ak times z to n minus k, which is nice. I have b0 times z to n plus b1 z to n minus 1 plus and so on plus bn times z to n minus n, which is 0. A0, A1, z to n minus 1, and so on. Not B. A0, let's take it over. A n. Evidently, this is a polynomial or rational polynomial. In complex plane, or yes, complex numbers z, meaning that now I have on nth degree polynomial, I have exactly n roots. Okay. Exactly. N complex roots. And the numerator polynomial roots of numerator, they are actually zeros of the system. Nullstellen. Nullstellen. I think spelling might be wrong, but anyways, and that's the zeros. Zeros of the system and roots of denominator term. This form I have then basically what comes out is B0 over A0 and then a product of how does it go? Okay. Z minus ZK product Z minus PK. K from 1 to n, K from 1 to n. Okay, so I have n polynomial roots here and n polynomial roots there. Zeros and poles. Zk and these are the pk. Good. What to do with the roots? That's one way of actually doing what to do with the roots. Graphical presentation. Graphical presentation of a system. Zero pole plot or Argand's diagram. These are complex numbers, meaning that I have the real axis and imaginary axis. Unit circle actually means something. Distance is 1, okay. Sometimes actually, well, if this was a Argand's diagram, then we would have the system total gain would be marked here, B0 over A0. On zero pole plot, it doesn't actually show you the whole system. It's missing the gain of the system, which is B0 over A0. Okay, so in here we can mark the zeros, usually inside of the unit circle, for example, like that. Third degree system, meaning 3 zeros or poles or both of them. Okay, that's different. Doesn't matter. And then we might have the sorry. Those are poles. Ah, how come I came up with the? Let's make it that way. Zeros usually on the unit circle and poles inside of the unit circle. All right, because of the stability. So if all poles are inside of unit circle, then system is stable. Bounded input, bounded output stability is guaranteed for LTI system which has all poles inside of the unit circle. The zeros can be anywhere. You can get most of the system if you put the zeros on the unit circle. Okay, graphical presentation. If you have multiple pole, then you would actually mark it with the number 2 or multiple 0, or well, mark it number of n there. Good. Wow, graphical presentation. Oh, why do I have? Wow, I have system. And there, okay, I have an example of the 4-point running average filter. Basically, I have this first the feed-forward version. Just do the math. You will get the zeros, 3 zeros, 1 here, another there, third one here. Poles for the polynomial coefficients 1, 0, 0, 0 would be just z to a power of 3 there on the denominator. Then you have a triple pole at the origo, since you have exactly the number of roots as the polynomial coefficient says. It can be then multiple. Okay. That's the one way of showing it. There's also another presentation. That was the feedback presentation. Okay, it doesn't show up. Well, maybe I should actually go and let's think. Yeah. Zeros and poles. Three-point running average filter was also h of z equals, that was 1 over 4. Here we have 1 minus z2 minus 1. Right, and upstairs I have 1 minus z2 minus 4. I think that was the system, right? Maybe. Let's go backward a little bit. Okay, yeah. Transfer function 1 over 4. Yeah, there's a sign error. So upstairs we have 1. Okay, there. Minus c2 minus 4, and downstairs 1 minus c2 minus 1. First we make it a polynomial of with the positive terms. We still have this 1 over 4 here. Then we have, oops. So the numerator polynomial is z to 4 minus 1. Denominator in the polynomial is, let's see, z to power of 3, z minus 1. I made this just for fun, because, okay, calculate the zeros. Z to 4 minus 1 equals 0, which means that z to power of 4 equals 1, which happens on 4 different places. Meaning, actually, z to power 2 is either plus 1 or minus 1. Good. Basically, that happens on 4 different places. Real axis, imaginary axis. So there you go, z equals plus or minus 1, or z equals to plus or minus j. Good. So the zeros are on those spots. Plus minus j and or plus minus 1. Poles, z to power 3 times z to minus 1 equals 0, means that either z to power of 3 is 0, which means that I have a triple 0 point still in here, or z equals 1. So we have a pole also there at the same place as we had a 0, which makes kind of sense when you're looking at, let's see, that one. So without that point, we would have exactly that feed-forward system for running average. We added z to minus 1, both upstairs and downstairs. So we added 0 and pole at the same place. Okay, good. So makes sense. Yeah, so this actually cancels out on frequency domain, but of course on the time domain it makes a big difference on how to do the calculations. And yes, stability. I also already stated that, okay, if all poles are inside of the unit circle, the system is stable. If any of the poles are outside of the unit circle, the system is unstable. Critically stable basically means that it's on unit circle. Critically stable system is similar to the analog critically stable systems. They are oscillators. Very useful, but hard to handle actually on digital domain to put exactly on the unit circle, since the rounding errors usually cause that pole to actually shift outside or inside, meaning that you either have a damping of the system or unstable oscillator. Good, but zeros can be anywhere. Whoa, that's all heavy. All right, and it gets a little bit heavier. Let me